Honestly speaking, no. I'm thinking about it. I have been thinking about it, but not really. No.
Yeah, it's fun. It's very good for summer student projects. It gives them a lot of motivation if you tell them, you're using a quantum computer versus you're solving some, topological Hamiltonian. Although maybe it is eventually the same, but for them it's like sounds more
exciting.
Yeah. So that's
okay.
So Emmanuel, the students really pick up very, very fast. Our students who are just beginning, like bachelor's, BSMS students, they pick up the IBM, quantum computer, use it, and start playing around. They really enjoy it very, very quickly.
Yes. Okay. Actually, so by the way, I have an important question regarding this specific lecture. So, should I suppose that the students know a little bit about quantum circuits? Say, if I say Hadamard gate, do they know what I'm talking about, or should I?
Yeah, you can actually repeat again, because yesterday evening there was a tutorial about that. Using this IBM quantum computer, but you still can repeat, not a problem.
Okay, good. Okay,
I think we have a lot of time.
I try to have something about the IBM quantum computer, so it's good that you have seen it yesterday, and then today I'll sort of connect to that. I will start slowly.
Yeah.
I think we have 30 minutes question session, and which means that you can overshoot your time a little bit, and it doesn't hurt us.
Okay, great. Yes, I will.
Okay, so should we start? Okay.
I'm ready. Yeah.
Okay, great. So it's a pleasure to have Professor Emmanuel Della Torre from Bar-Ilan University. His primary interests and expertise are really on quantum simulations with, quantum dynamics, essentially, of many-body quantum systems. And since his PhD, I think he has been working on this field. He has done his PhD from Weizmann Institute of Science, after which he moved on to Harvard University for a postdoctoral fellowship where he stayed for a while, and then he came back to Israel as a faculty member in the Bar-Ilan University. And with that, I hand over to Emmanuel for his talk. So the title of his talk is Quantum Simulations with Quantum Computers on the Cloud, Floquet, and Topology. Emmanuel, please.
Okay. So Surin, thanks a lot. I don't see the live or recording message, so I'm not sure if this is recorded, but
I believe, it's on the, I believe there's a, Prashant, is it being recorded?
Yeah, it is being recorded, and YouTube broadcast is going on.
It's broadcast, yeah, right.
Okay, great. Okay, so let me share my screen and then start. So I understand that, first of all, thanks for the invitation. And, I'm just sorry that I cannot be there physically, but I hope that this can happen soon. So here in Israel, as you may have heard, the COVID situation has improved a lot thanks to the vaccination. Actually, today is the first day that we don't have to wear masks, even in closed space. And I know that in India, the situation is for the moment still not very good, but I hope that as in the same way that we were able to get rid of this virus, this will happen in other parts of the world, and in India as well. So I understand that we have sort of an hour and a half. In principle, it's a lecture for us questions. If you would like to ask questions in the middle, that would be great. Just feel free to stop and at any time. The only thing is I'm not looking at the chat. So if you want to say something, feel free to do that. Just unmute yourself and speak. Or otherwise, if you write in the chat, I would kindly ask one of the organizers maybe to read what's written in the chat. I'm just not looking at the chat. Okay. Yes. So first of all, this is my group, which has grown quite a while recently, and this is mostly thanks to these quantum computers that attracted a lot of interest among young students. This is a picture that was taken last week in my place. So as you see, we're not wearing masks. This is nice. And I acknowledge the financial support of this Israel Science Foundation, and also a collaboration with private research partners, and in particular the group working on quantum computers in Israel, mostly the IBM group, and more recently also the Microsoft and the Amazon. Also, they have opened a small research group in Israel. So this is great to be able to collaborate closely to people that have access to the systems themselves. And I also acknowledge help from the Inter-University Computational Center. Okay, so I think the one thing you all know if you are here on in this workshop is that quantum computing is a reality. I was very skeptic about this field, and when I spoke about it 5 years ago, I had the feeling that it's going nowhere. But I think that by today, we need to acknowledge that quantum computing, and in particular quantum computing on the cloud, meaning being able to connect to a quantum computer remotely is happening, is a reality. Something that we need to know as physicists. So in order to understand this work, you need to distinguish between portals, basically services that allow you to connect to a quantum computer and hardware. It's companies that really create the quantum computer themselves. So the pioneer in this field were actually IBM, who both built the quantum computer and gave access to it. And understand that you had already some introduction yesterday about IBM quantum computers. I'm going to recall it in a moment. But more recently, there are other companies that both build quantum computers and allow you to connect them. So the largest portals are Amazon and Microsoft that do not have quantum computers of their own. Amazon, I know that Amazon and Microsoft are working on building one, but for the moment, they don't have a quantum computer of their own, but they allow you to connect to quantum computers. And there are two main types of quantum computers, superconducting quantum computers and ion quantum computers. We'll mention that later on. But for the moment, it's just important to understand what is, who is offering a service, which is just a portal or a software, we would say, and who is offering the hardware. And these are the main names. And I think that it is in the next few months, probably more names will add. So let me give you as an example, the example of IBM quantum computing. And I understand that yesterday you had a short introduction to this field. So you basically go to this website, you register, and you enter. And when you enter, you're offered a choice of quantum computers available on the cloud. This is the largest one that is available for free to everyone. Actually, it's going to be closed soon, or it's going to die soon. This quantum computer. For the moment, it is still online. It's an old one. I mean, the quantum computer is about four years old, so it's not the best most proficient one. The one thing I would like to mention, so there's a lot of information about these quantum computers, but let's focus on the most important details that we are interested about. So first of all, you see here on the bottom right, you see here these quantum the qubits. So these 0 to 14 are 15 qubits. So each circle is a qubit. And actually the color is interesting because the color refers to, say, the error. So you see these bonds are the gates. So you can apply gates between any neighboring qubit. This is going to be important in a moment. And the gate have different fidelities. So you see there are some purple gates that have a low error, a large amount of error. There are some more dark gates that are lower error. So there are variations from qubit to qubit. And just let's take an average. So on average, you see there are these two parameters. One is called average C0 error. So this is the error of a 2-qubit gate. And you see it's basically 4%. So this is about 4%. Another source of error is measurement error. So if your qubit is in 0, 1, you try to measure it, sometimes you get the wrong answer. And here it's 6%. So this is not state of the art. I'll mention in a moment what is the state of the art, but this is for a sort of an old quantum computer. It has 4% on a 2-qubit gate and 6% on a measurement error. So let me give you an example. Have you seen this sort of screen or of software yesterday? Yes, no?
Emmanuel, most of the students, I think, are on YouTube, so probably they can only kind of type in it, and they cannot respond you directly. Only a very limited access is there for the Zoom. Yeah.
I see. Okay, great. So I think you probably have, because I mean, this is what the standard.
Yeah, many of them are typing yes. They're just to
yes.
inform.
Okay, great. Okay. Thanks a lot. Sorry, this is very useful. So yes, excellent. Okay, great. So let me give you an example. Maybe this is the same example that you've seen, but nevertheless, let me show you how it works. So for what you can do, you can basically drag and drop an Adamant gate, which prepares for you a superposition of 0 and 1. Then I apply a 2-qubit gate, which prepares basically superposition so the Adamant gate prepares a single qubit superposition, and when you apply a control NOT gate, then depending on of the state of the first qubit, the second qubit is either inverted or not. So what you end up is in a situation where you have either 0, 0 or 1, 1, and of course this either or actually refers to a superposition of 0 and 1, and actually you can go on, sorry, let me repeat the movie. So again, I prepare a single qubit superposition, and then I drag and drop a control NOT gate. Now I'm going to drag and drop another control NOT gate. And what it does for you, this is actually preparing what I would say is like a cat state. So a cat state is just a state in which you have a superposition of 0, 0, 0 and 1, 1, 1. And then you can run it on an available quantum computer. So here I'm just using free qubits. So there are many quantum computers with free qubits that I can use. You see that on the right, there is actually the code. This is some language for quantum computing, which prepares free qubits and then applies these gates. So that's what is done. The reason I'm bringing this is actually I'm really interested in what's going on in reality. So first of all, first message is that you need to wait time. We are used to say that quantum computers are really fast. Actually, no, they're quite slow. It takes a lot of time because you need to connect to the queue. You need to wait in the queue. Then process the quantum. So it's not, the speedness when you compare it with 2.1 gigahertz Intel microprocessor. It's actually these quantums are very, very slow. But okay, we know that they may have possibilities that go beyond classical computers. Okay, so when you have waited long enough, you get the result. And let me show you the result. This is what I'm interested in here. So remember what was the theory. The theory was 50% 0, 0, 0, 50% 1, 1, 1. That's just the circuit that we prepared. Now there are two differences. Difference number one, as you can see, you get also some states that you are not supposed to get. You get them. So you were not supposed to get 1, 0, 0, but that's what happens sometimes. And also, and this is due to two reasons, as I mentioned. First of all, when you prepare the state, there may be errors in the gates. And second, when you measure them. And the measurement error is interesting in particular because you see that there is a discrepancy between 0, 0, 0 and 1, 1, 1. So there is a higher probability of measuring 0, 0, 0 than 1, 1, 1. By the way, you see also this is the reason why you get this 0, 1, 1, 1 with high probability. Probably this was supposed to be 1, 1, 1, but then one qubit, instead of giving 1, it gave you 0. And this asymmetry is related to the hardware itself. So the hardware is, you can think of it, it's a bit more complicated than that, but think of a single photon detector. So a single photon detector, if you don't see a photon, there could be two reasons. Either because there was no photon, so that you say you are in the 0 state, or because there was a photon, but you haven't seen it. So as you see in the single photon detector, there is a tendency towards 0. It's more probable not to see the photon, either because it was not there or because you haven't seen it, than seeing 1. If you see a photon, then okay, sure, I'm sure that there was a photon. So you see there is an asymmetry between 0 and 1. Now the quantum computers work a little bit differently, but the concept is the same, that the state 0 and state 1 are physically different. So there could be a difference between, a higher probability of seeing 0 than seeing 1. Okay. So let me put together the numbers, because I think this is important in order to evaluate what can we do with those quantum computers, which fidelity do I need. So this is a thumb rule. So the thumb rule goes as follows. We have seen that you have a gate error of 40%, a measurement error of 6%. That means that it's about 10% per qubit. So let's assume that, just take a number of gates as the number of qubits. So this is the simplest thumb rule you can build. So you get 10%. So that would mean that if you want to run a protocol with say 3 qubits, like here, there are 3 qubits, then you would get a 30% error. And this is consistent with what you see in this experiment. You see that if you sum up all the errors, all the wrong answers, you get about 20, 30%. So this is a way to estimate how many gates could they put. So what you understand is that if I'm trying to use all the 15 qubits I have, then the error is 100% error. There is nothing left here. So as a thumb rule, I would tell you the following: take how much qubit error you have per qubit, in this case 10%, multiply by the number of qubits. When you get to 50%, then you can throw away your quantum computer. So in this case, for instance, for these error levels, you can do something useful with, say, 5 qubits. More than that is quite useless. So if you have a 10% error, then you can do something useful with 5 qubits. Of course, if you had a 1% error, then then you could work with 50 qubits. That's already something, 2 to the 50 is a big number. So that would already be something useful. But you need to have many qubits with a little error. And here you have, 2 large errors. So for instance, this is an example of a recent paper where they were able. So you probably all heard that what you can do with a quantum computer is to factorize big numbers. I'm sure you have all heard this story. And so the question is, which number can you factorize? Turns out that in this case, it's about, so the largest number is 21. So they can factorize 21, right? It's 7 times 3. And I'm saying this because 21 is, if you have 5 qubits, you see, they can use 5 qubits, then the largest number is 32. So you can factorize, let's say. 32 is boring. So 21 is sort of an interesting number, this more than 32. So, but I'm bringing this example to tell you, what are the orders of magnitude? Which errors? How should I read the fidelity of the computer? So I'm saying take the error and multiply by the number of qubits. If you get in the order of 50%, that's useless. Okay, good. So what is the main challenge? So the main challenge that I have introduced you is this dichotomy between the way we try to think about quantum computers in theory, which is just, unitary gates, these circuits, Hadamard's, Control Z, all these gates, T gates, Y gates. So there are all these nice gates, and we build protocols, we build the Shor algorithm, we do quantum machine learning, we do all sorts of interesting stuff. And on the other hand, this is one hand. On the other hand, there are the reality. Reality is that the noisy quantum computers, say in this case, superconducting circuits, which are even more noisy. You can maybe have a lot of qubits, but it's useless because they are so noisy. And the question is how to bridge the gap. Okay? This is the main challenge. And we don't know, will we be able to bridge this gap or not? That's something that will be answered within 10 years from now. Only in 10 years from now, we will know whether we have been able to bridge the gap and bring these quantum computers to doing something very useful. And there are 2 ways to proceed, and you need both ways. Way number 1 is to say, well, let's improve the hardware. If the hardware is not good enough, you need to improve it. And for instance, you can apply what is known as quantum error correction. So quantum error correction is an algorithm that allows you to take many noisy qubits and make a better qubit, so a better logical qubit. So you can say use the numbers or something like take a million noisy qubits, and you can make a good protocol with it becomes equivalent to a protocol of a good 1,000 qubits, something of this. These are the orders of magnitude. So you can think of, the simplest case is just a repetition code. So instead of you encode each qubit in many qubits, and then you take the average. And so you know that the average will be closer to the correct result if you just average over many qubits. So this is the simplest code. Of course, there are more advanced topological codes, etc. But the idea is always the same: to use, to improve the hardware so that eventually you end up with this unitary model of quantum computing. The other way to proceed is to say, I would say the other method is more like the first one is more computer science oriented. The second one is more physics oriented. And in physics, we say, well, if the model doesn't describe the reality, well, then you should improve the reality. Right? That's what you do in physics all the time. We have a very material, and we try to model it, and we need to improve the model so that we describe the material. And so this is, in particular here, what you really need to study are open quantum systems. Why? Because you need to describe the noise, and you also need to describe the dynamics, right? What you are doing when you work on a quantum computer, you are basically taking circuits and applying some microwave pulses. You see all these lines here, all these wires are just wires that bring the microwaves into the quantum computer. So you really have a quantum system on which you apply a drive. It's really an open quantum system, both because there is noise and because you drive it. So what you really have is the paradigm of open quantum computers and also of open quantum systems. And that's something that we physicists have been studying for long times. And I think the knowledge that we have accumulated on open quantum systems can be helpful to benchmark quantum computers, maybe even to make something useful out of quantum computers. So the typical paradigm of an open quantum system is made of three parts. Oh, I see there is a typo here. So there is a quantum system, which is coupled to some environment. This is typo. And it's missing. Okay. Anyway, and on the other hand, there is the drive. And the system is really often found in some steady state when you have the drive on the one hand, the environment. So the environment could be of different types. It could be, say, a quantum environment, like quantum buff. It could be a classical environment. For me, in the context of quantum computers, the environment is usually the measurement device. And actually, the measurement device is very important. You may be familiar with something called topological quantum computers. So something in which you use topological qubits. But the problem is that they are very good. They're protected. They live forever. The problem is that something that is very protected, lives forever, you cannot access it. Right? That's the idea. How you make something very long-lived by isolating from environment. So say there was no environment. Right? Say that I can build a beautiful quantum computer with no environment at all. Just the perfect quantum computer. The perfect quantum computer is useless because you cannot measure it, you cannot couple it. So being able to measure the quantum system is important. This means that the environment is important. So what I would like to do here, so this was the introduction, sort of a lengthy introduction. I think it's worth because eventually this is cool. So what I'm going to do now, I have brought 3 examples. We'll see if time allows us to go over all the 3 examples. Maybe I'll speak only about 1 or 2 of them. These examples are not extensive. These are just the things that we were able to do in our group. And I'm sure you will hear more during the school about other examples. So this is not, this is just some projects that we were able to do on the quantum computers. And these 3 projects, I tried to relate them to the 3 parts of the quantum computer. So the first project is more related to environment, let's say to the measurement apparatus. The second part is more about the quantum system itself. And the third part, we'll see if we have time, is about the drive. Okay, so this is what I have to do. So I see there is a question here in the chat. The question: can we associate the asymmetry to the factor that detectors are not 100% efficient? Reference CAT preparation slide. Yes. So about this. So first of all, any error means that detectors are not 100% efficient. That is right. And but there are 2 types of inefficiency. It could be that I don't see a photon when there is a photon, or that I see a photon when there is no photon. So they are both type of inefficiency in a sense. It's just that because in this case, the type of effect of inefficiency, meaning that you don't see the photon that was there, is more pronounced. That's why you see more 0 than 1. So I would say the answer to the question is yes, absolutely. That's exactly the idea. Okay, good. So let me give you let's start with the first system. So I don't know if there are more questions in YouTube, then I don't see them. So I would ask the organizers to maybe bring them here.
Yeah. I think Sohan has asked a question. He's saying instead of using superconducting wires, can we use EM waves for designing a quantum computer?
Okay, so I think the question is why are we using microwaves, right? Eventually, the superconducting circuits are eventually tuned by microwaves, and you can say, why don't you use optics? So the answer, let me first tell you what is the big challenge. The big challenge in using optics is that it is maybe easier to create interesting quantum states of light, like a single photon state, because you don't have noise, right? You don't need to cool to room temperature. The temperature is so low. If you work at optical frequencies, then the temperature is so low with respect to optical frequencies that basically you can think of not having any photon from the environment, even at room temperature, which is great. So it's easy to prepare interesting photonic state. What is the problem? The problem is that electromagnetic waves, by definition, are linear. Maxwell equations of motion, that's something very important. Maxwell equations of motion are linear equations of motion. That's why we teach them in undergraduate, because they are linear. So this is nice, but it's not useful to build a quantum computer, because the quantum computer requires an interaction between the qubits. And interaction is basically nonlinearity. And if you want to have a gate, a good gate, you need a strong interaction. Something that where the interaction is at the same order as the frequency of the qubit itself. So you really need very strong interaction. You need to be in what is known as the strong coupling limit of optics. And this can be reached. Basically, the way that you reach it in general is by having some atoms, because the atoms are nonlinear. In the sense that, say, if you excite an atom, then you cannot excite it anymore, right? It's like a two-level system. It's something very nonlinear. You cannot, once you excited it, you cannot excite it anymore. So exciting it twice is not like twice exciting it. Okay, so, but you need to be in the strong coupling regime where you can couple a single photon, single atom. And that's very hard to achieve. So people, there are ways to do it. And actually, there is a company building a quantum computer based on photons. I think it's called the PsiQuantum. It works on a different principle. It's based on the idea of measurement-based quantum computers. And the problem, again, so in principle, it is possible, and it is also plausible, if you ask me, that maybe we will end up in a quantum computer that have a different technology. So if you think about transistors, and you remember the first transistors that were huge, and they were not based on semiconductors, right? Eventually, it was the technology of semiconductors that led us to having these microcomputers. So it is possible that maybe there is another technology that is still beyond the horizon, which will bring us to these real working quantum computers. And maybe these photons are the way to proceed. For the moment, we are not there yet, but people are working on that. So it is possible, and maybe it will work. But then you really need to go into the details, of how you make it work. Other questions?
There is one more question which says, does machine learning could help in quantum error correction?
So yeah, this is a huge question. This is an excellent question, which is about the relation between machine learning and quantum computers. Actually, they are often, if you look in the newspaper, the popular science articles, they often come together, right? Okay, quantum computers and artificial intelligence, they come together as a sort of leading technologies. So of course, machine learning can help a lot, and it can help in different ways. First of all, it can help you building a better circuit. So let's say, as I mentioned, the quantum computer is built by activating some microwave pulses. And the question is, what is the optimal set of microwave pulses that will lead to some specific gate? You see the number of parameters is huge. You have 2 qubits, and you can send any pulse you wish to any of the qubits. So it's a lot of freedom. And when you have so many freedom, it's very hard to make an optimization, say, analytically. So machine learning could help doing that. It could help building a better gates. That's number one. Number two, that's actually something I have a little bit worked on. It's not here in the presentation, but it would be to use quantum computer, so machine learning for error mitigation. So error mitigation means that it's basically an idea of post-processing the data. So I have measured the quantum computer. Now, for instance, I know that 0 is more probable than 1. then I can fix it, right? Then I can probabilistically fix it. And when I see 0, well, sometimes I keep 0 and sometimes I move 1. This will give me a better description of the reality just because I have some knowledge about the quantum physical quantum computers. So what about this is for a single qubit. It's very simple. But if I have many qubits, can I also mitigate the errors by post-processing the quantum, the data, the measurement in a classical machine learning circuit? So can I use classical machine learning to improve the readout of the quantum computer? So these are two different ways to proceed. Maybe there are more, but these are two ways that I'm familiar with. So yes, machine learning could really help. And the reason is that the quantum computer has a lot of parameters. And whenever you have a lot of parameters, then machine learning can help you doing a better optimization. This is not what I'm going to show here, although it is a very interesting direction. Okay, so what is the question? So one question that one may ask is, can I show some sort of quantum advantage with noisy quantum circuits? So quantum advantage is a tricky word. It can have different meanings in different contexts. Some you probably have heard about quantum supremacy. Some people don't like the word supremacy because of the political connotations. So some people use quantum advantage as a synonym of quantum supremacy. But here, let me define what I mean by quantum advantage. What I mean here by quantum advantage is to show some effect that is really quantum. To be able to be sure that it's really quantum mechanics that we are playing with here, and not just some complex classical system. And you probably all remember from your courses, your undergraduate classes of quantum mechanics, that this question was a big question about, at the beginning of quantum mechanics. How do we know? Quantum mechanics is a theory. It's a nice theory. I know how to describe it. But how do we know that reality really follows quantum mechanics rather than classical, stochastical equation of motion? And you all know Einstein's the problem with the dice. God doesn't place dices. So it was a big debate, but eventually the debate was resolved by an experiment, because in physics we are experimentalists, so we come to the reality and we look at the realities. Do you follow quantum mechanics or classical mechanics? And the way to do that was to basically through these Bell inequalities. So Bell inequalities are some relations that are agnostic of the details of the system, but tell you if the system is classical, then there will be some property of the system. And the question is, can we extend it to many qubits? And this is the resilient to noise or not. And so one solution is the idea of using non-local games. It's fun because it's a game, and that's why I chose this to be the first topic that I wanted to describe. And in particular, I would like to focus on one game. It's called the triangle game. It was introduced by Bradley, Kostet, and Koning in this science paper in 2018. The paper is really tough. It's really hard to read the paper, but there is a beautiful PRL by Daniel and Nyaka from this year, where they extend this analysis, but first of all, they explain the game in a language that is easier to understand. So I like this. Both papers are nice, but if you want to actually learn about the game, I would advise you to start from the PRL. It's easier to read. Then you can go back to the science paper. So this is a game. I'm going to describe the game in a moment, but it's a game that has many players. That's why it is an extension of the Bell inequality. The Bell inequality between two qubits. Here we will see that we have many, many qubits, at least 6. The minimal number of qubits to doing a triangle game is 6, because each player has 2 qubits and you want to have a triangle. So the minimal instance is to have basically 6 qubits. Three players that are in a triangle and 6 qubits. But this can be extended to any number of qubits. And the game is defined in such a way that if the players are classical players, they can win only 7/8 of the times. I'm going to explain a little bit where this 7/8 comes from. But for the moment, remember that this is the number, 7/8. And in contrast, the quantum computer can win 100%. So if you play the game and you see that the players win more than 7/8 of the times on average, then you know that it's a quantum. These are quantum players. So how does the game work? So first of all, this is a collaborative game. What does it mean? It means that the players work together. They're trying to win, and the winning means to satisfy some conditions. So there is a classical dealer which sets some conditions, and the players are trying to win by satisfying all the conditions. And they can decide, they can talk together before starting the game, and they can decide on some strategy that will allow them to win. So naively, it looks simple. I mean, if you know what the rules are, then you just you sit down at the table and you choose some strategy to win. What is the problem? The problem is that actually, while playing the game, each of the players tosses a coin. Okay, 0-1, tosses a coin. And the coin actually affects the rules of the game. So the rules of the game change depending on the results of the coin. And what is the problem? The problem is that the players, when the game starts, the players are not allowed to talk to each other. This is the no locality, okay? They are no local. So each player lives on its own. So it tosses the coin and is not allowed to tell the other players what is the result of the coin. So you end up in a situation when you know what is the result of your coin, but you don't know what are the results of the other coins. As a consequence, you don't know what are the rules of the game, and hence you cannot win always, because you can choose a strategy that will allow you to win many times, but not all the time. So this is the table of this specific game. I mean, there is nothing very crazy about this. These are just the rules that were set by this game. You can change them, but these are nice rules. And the rules are such that, so first of all, what you see are 8 rows, 8 lines. And the 8 lines refer to the 8 possible outcomes of the coin. So say 0, 0, 0 if all the 3 players get. So depending, as I told you, depending on the result of the coin, you will need to satisfy different relations. Okay, so either x1, x3, x5 is 1, and x2, x4, x6 is 1. This is if you get 0, 0, 0, or if you get 0, 0, 1. So you see the roles depend on the coins, and what makes the problems, are this -1. That in some situations you need that some of these Pauli operators, x and y, give you some minus. So you cannot just put plus on all the results. Sometimes you need those minuses. And so what you can see, it's quite straightforward to see. If you can see that you cannot satisfy all these rules at the same time. So if you satisfy, these rules cannot be satisfied all the times, and that's why the classical players cannot win all the times. The best strategy is to basically get rid of one rule, not satisfy one rule, to forget about one rule, satisfy all the other rules. That's okay, that's possible. And in this case, you will win if for all these results. So for the first result of the coins, you lose, but you win for all the 7. That's why the classical players can win 7/8 of the time. They win for all the results of the coins except for the first one. That's the best classical strategy. Actually, the classical strategy is very simple once you do it. Okay, so this is the classical game. Okay, why? So that's not very interesting. What is interesting is that actually you can do better with a quantum computer or a quantum system. How? So the idea is that before the game starts, you prepare all the players in a correlated state. So you see, I have prepared all these qubits. Each qubit, all the qubits of the players, I have prepared them in a particular state. Actually, this state is called the cluster state. We'll come back to this specific state in a moment. It's called cluster state, and well, the idea is that so you have an entangled state of all the players. Next, what you do a measurement, and here comes the fundamental part. The measurement will depend on the coin that I have, on the result of the coin. So what they do, each player tosses a coin and then measures a measurement that depends on the coin. And now you see the trick. What is the trick? The trick is that in quantum mechanics, when I measure X or Y, I have not locally affected the other players. The results that when I measure something here, I affect the result of the other player if the 2 players are entangled. That's exactly the idea of the Bell inequality, right? The Bell inequality tells you that when I measure one qubit, I am affecting the other qubit. And this is exactly what happens here. That by measuring one qubit, I am affecting the other qubit. And that allows me to win with a higher probability. So that's the trick. The trick is I prepare the players in a correlated state, in an entangled state, and hence by correlating the measurement with the result of the coins, I am as if I am telling the other players what was the result of the coin. I'm not really doing that. You're familiar with this paradox that actually you cannot transmit information. So I'm not really telling them what is the results of the coin, but I do affect the measurements. I do affect, there is a no local action in distance, and that's what allows me to win 100% of the time. At least, this is if I had no noise, in theory, in the ideal model. What happens in the real model is that there is noise. So what we did, we tried to get rid of the noise a little bit by doing this post-selection or post-processing of the data. Of course, the post-processing doing locally. So each of the player is doing a post-processing on its own qubits because they are not allowed to talk to each other after the game has started. Okay, good. So let me get to the result. Okay, so the result is following. What I'm going to show you are the results of 4 quantum computers. This 7/8 is 87.5%. I used to say that in each talk there is one thing that you learn from the talk. So in this talk, what you will learn is that 7/8 is 87.5%. So that's the quantum advantage. So if I get a result that is above the red line, then it means that the quantum computers are quantum. They're not just classical computers, they're quantum computers. If I just play randomly, I could get to 37.5%. So let me show you the results. These are the results from 2 IBM quantum computers with superconducting circuits and an ion queue, so the quantum computer of ions of the ion queue, and the quantum computer of ions from Honeywell. And as you can see from here, actually, all the quantum computers fail the test. So according to this test, you cannot be sure that these are quantum computers. The noise is too big to demonstrate a quantum advantage for this specific probe. So these are the bad news, or maybe the interesting news, because it means that actually we need to improve our quantum computers. There is still work to be done, which is great news for the students. We need you. We are not there yet, so we need your help to get there. So that's point number 1. Point number 2, actually, after we posted this paper online, we got a very nice email from Honeywell, and they told us, well, we have the H0, which is the first quantum computer, and this is the one that you used, but actually there is also an H1, and the H1 has a much better proficiency, and although I cannot disclose the results, let me just tell you that the H1 actually does show quantum advantage. So the results of H1 actually are below the red line. So this is really great. Things are happening right now. And the second part is actually the strategy we choose in the paper, because in the manuscript we didn't know that we would be able to do that. So there are some students in the audience, but there are also some professors. So as a professor, that the students fail. What you usually do, you just lower the bar, right? There is no way. At least that's what we do in Israel. So we lower the bar, and so the idea was, okay, if all the quantum computers fail this test, maybe we can have a better test. We have a better, instead of having, let's say, the quantum advantage instead of 7/8 will be, say, 1/2. Then everyone can win the game, and that's indeed what we did. I don't want to go into the details, but if you are interested, maybe at the end when you ask the questions, I can ask you. Let me just tell you that we thought about such an inequality. So just another inequality, and the other inequality is that something. Some expectation value must be smaller than 19. Right? That's the result, the classical result. While in the quantum case, it would be 55. So it means that the optimal the advantage is reached not for 7/8, but 19/55. So it's even below half. So that's much easier to reach. And indeed, when we run it on an IonQ quantum computer, we get 41. So 41. It's about 80%. So we are still in the order. The quantum computer is still of the order of 80%, like here. Remember, all the quantum computers are about 80%. The problem is that the bar were 87.5. So we lower the bar to much lower, to 19/55, and so we can get to the threshold. So it also means that different tests can detect, there are some optimal tests that can detect more easily quantum correlations. And that's what we did here. The problem here is that it's not easy to extend it to many qubits. So the non-local game of Bravi, the beauty there, the triangle game, is that you can easily extend it to many, many, many players. Here, in contrast, you cannot. So there is an interplay between, on the one hand, how many measurements you need to perform. See, you need to perform here more measurements, actually 55 measurements. So there, in that case, it was only 8 measurements. Here we need 55 measurements. And if you increase the number of qubits, we need more and more measurements. So it becomes harder and harder. But on the other hand, it's easy. So, there is an interplay between how many measurements you perform and how precision you need. And so these are things that we are now studying. Okay. So Surin, are there other questions in the audience?
Not really. Not any serious one.
Okay.
You can move ahead. Yeah. Hello?
Yes.
Emmanuel, none. I don't see any serious questions. So yeah,
okay.
Please.
Excellent,
yeah.
excellent. Okay, let's go ahead. We will then stop for more questions. Yeah. Okay, good. So let me now tell you about the second project. It's sort of unrelated, although as you will see, actually, it's sort of actually this work was sort of previous. Historically, we first got to the more complicated one, and then we did the easier one. But I chose for the didactic purpose to first show the simpler one, and then to go to the more complex one. Okay, so the more complex one is about studying topological phases of matter using a quantum computer. So what is the idea? The idea here is, can we do something useful for quantum computers? And in particular, can we use quantum computers to simulate some complex physical effect? Okay, so let's forget about algorithms. Let's forget about Shor and numbers. Let's think of this as a quantum system. Can we use these quantum systems to simulate another quantum system? So what we proposed in particular was to study an effect that is very important in physics. I guess most of the people in the audience are physicists. So you all heard about the quantum physics of matter. You all know, I guess you have all heard about ferromagnets, antiferromagnets. We don't need a deep understanding. Just to say that in physics, we can classify all the phases of matter as order and disorder. The most well-known example is glass. You all know that in glass, all the molecules sit on a lattice. They are ordered. That's why glass is, ice, of course. Ice is, in ice, all the molecules are ordered. So that's why it is a crystal, it's a solid. While when you heat it up, it melts and ice becomes water, and more water, the molecules are disordered, and that's why it becomes a liquid. So basically, the simplest example of a transition from order to disorder would be the transition between solid and liquid, say between ice and water. By the way, I mentioned the glass. So glass is also related. Glass is an example of a disordered phase. Actually, that's something that people may not be familiar with in a glass, like just the glass of the window. Actually, all the molecules are disordered. So actually, glass is an example. It's interesting because it still looks like solid, right? Glass it's solid, but it's disordered. So naively, when we learn in high school about solids and liquids, we think that all the solids are crystals and all the liquids are disordered. But actually, it turns out that there are examples of phases that are disordered and still sort of solid, like glass. We can build a big window, so it's certainly not liquid. People say that it's just a matter of time. Maybe if you wait long enough, then your windows will eventually melt. But no one has ever seen such a thing. It will take maybe the life of windows. Okay, but this was unrelated. So okay, so we have what I have told you is that all phases of matter can be either ordered or disordered. If you would use the language of qubits, an example of an ordered phase could be, say, a string of qubits that come 0, 1, 0, 1, 0, 1. So there is an order. It means that if I know what is the value of the first qubit, then I know that the value of the 1,000,001 qubit will also be 0. So this is known as long-range order. Knowing one qubit at the beginning, I know what is another qubit very far away. In contrast, in a disordered phase, that's not the case. 0 and 1 come randomly, and well, they have no information about what's going Okay, now this was true. What I told them until now was true until 20 years ago. Now, in the last 20 years, mostly in the last decade, people understood that actually there is a third type of phases, which are known as topological phases. Of course, there were hints already back in the 80s for the work that Duncan Haldane was awarded a Nobel Prize. Here I have a joke that I learned from one of my teachers that everyone that you give a presentation, there should be a Nobel Prize next to your name. So that's how I achieved that. So of course the Nobel Prize was related not to my work, to work of Haldane, and what he discovered was an example of topological phases in one dimension. And let me give you an example, so the pictorial example of such a phase in 1D with qubits. So what is the idea? The idea is that topological phases look like disorder, but somehow they have some hidden order. And in particular, for these one-dimensional phases, what happens is that there is a string order, and the string of order tells you that although 0 and 1 comes randomly, the ones sort of pair together. Means that after, if I observe 1, 1, then there is a high probability of observing another 1 rather than 0. So not for even, but not for odd. So they sort of come in pairs, not always neighboring pairs, but they are closer together. So the state is disordered. Why? Because if I tell you that there is a 0 here at the beginning, I know nothing about what will happen in a million qubits. I know nothing what will happen for this qubit, back on the right. So this is disorder. There's no local order. There's no spontaneous symmetry breaking. I don't know. I have no information, but yet there is some particular type of order. And the way to look whether the particular type of order exists is really to look at the entire sequence. I need to look at the big entire sequence, and then we'll see whether the ones come together or not. If you just focus on 2 qubits, I know nothing. There is no order there. But it is really when you look at the whole picture that you see that there is order. So that's an example of a topological phase for qubits. Now, the question is, how do you realize it in a quantum computer? So what I would like to realize is examples of ordered phase, disordered phase, and topological phases on quantum computer. And here comes a very important message for physicists like people like Surin. Condensed matter physicists. So when we speak about condensed matter, what we have in mind is an Hamiltonian and the ground state. We tell, okay, the Hamiltonian is some interacting Hamiltonian, and then I ask myself, what is the ground state? So can I ask myself, for instance, is the ground state ordered or is the ground state disordered? Is it topological? That's the question that we ask. In quantum computers, there is no Hamiltonian, and in particular, there is no ground state. So the system is not in the ground state of some Hamiltonian. It is in some quantum state, but not in a state of Hamiltonian. So what you can do is what you need to do is not to engineer the Hamiltonian and then ask the system to go in the ground state of the Hamiltonian, but you need to really engineer the state itself. So the question is not, can I build an Hamiltonian such that this is the ground state, but rather, can I build the state itself? And actually, in the case of the ordered state, it's very easy. Okay, sorry. So first of all, this is the Hamiltonian. Okay, let me show you what are the Hamiltonians. So this would be an Hamiltonian whose ground state is ordered. This would be an Hamiltonian whose ground state is disordered because, okay, the ground state of this Hamiltonian is that all the spin point in the x direction, and if I measure it in the z direction, that it's randomly 0, 1. So this is something we would call disordered. And this is an example of a topological Hamiltonian. Here I put my own reference, not because we invented this Hamiltonian, just because I like my paper, but you really need to go into, there are many references. This Hamiltonian is a sort of a generalization of the Ising model. And it was found separately by many different authors. So I really refer you to the reference in this paper where we try to give a broad review. It was quite natural to think about this Hamiltonian. It's called the cluster Hamiltonian. And what I'm trying to say is that in quantum computing, what we should really look at is not the Hamiltonian itself, but rather the ground state. So asking, can I prepare the ground state of the Hamiltonian? So in the case of the Ising spin, it's very simple. Just do nothing, right? If you prepare all the qubits in the 0 state, then you did it. I mean, you have the ground state of this Ising Hamiltonian. How about the magnetic field? So for the magnetic field, I can also do that. And we just prepare all the qubits in an equal superposition in 0 and 1. We just apply Hadamard to the qubit. Very simple. How about the cluster state? It turns out that preparing the ground state of this Hamiltonian is very hard, is very easy. Preparing the Hamiltonian itself is hard. Having a physical system in which this is the Hamiltonian is something very hard. In contrast, preparing the ground state itself in a quantum computer is very easy. And actually, it is exactly the same cluster state that I have shown you before. So you just apply Hadamard gates on each qubit, and then couple neighboring qubits by control Z gates, and you did it. So it's a very shallow circuit, right? It's very easy to prepare. You just need very small number of gates. And you remember, applying many gates is a problem, but here we need to apply a few. Okay, so this is something that was done. Actually, I'm missing here a reference by the group of Titus Neupert, PRL from 2019. Maybe 2020, when they realized, we also thought about this Hamiltonian and discussed the fact that preparing this state is really the ground state of this Hamiltonian. So I'll end that. Ask me if you want. It is references in our papers, of course. Okay, so you can prepare that state. And the question we asked is, how can I convince myself that I prepared a topological phase, or in particular, what is known as a symmetry-resolved topological phase, or symmetry-resolved topological states. So this is a particular type of topological states. So let me show you a nice way that we obtained, that we thought about to characterize the topological properties of the system, which for me also was a way to learn about topological phase. So these phases are phases that require symmetry. And what does it mean? A symmetry means that there is an operator that commutes with your state. Right? That's the definition of state. So the ground state commutes with some operator. Now it's easy to show that if, but it's easy to show, but you really need to do that. I mean, I was not convinced until I did it on my back on the back of my envelope. It's easy to show that if there is such a symmetry, then the reduced density matrix, so you know what the reduced density matrix means, that you look at part of the system, will commute with the operator itself. In other words, the reduced density matrix is the block diagonal in the symmetry. So let me give you an example. So think of a symmetry which is just a Z2 symmetry. So there are two factors of the symmetry, say even and odd. Okay, even spin and odd spin. So what will, if there is such a symmetry, if the symmetry exists, then the reduced density matrix is diagonal, is block diagonal in the symmetry operator. And this is just a definition of a symmetry. Okay, let me give you an example. So think of the symmetry that is the conservation of the total number of particles. So take a box with 100 particles. Now, if I look at half of the box, in half of the box, say the particles are in quantum superposition. Okay, they are in entangled state in superposition in the box. When I look at half of the box, well, sometimes I find 50, but sometimes 48, 47. So the number of particles is not defined. In the total box, it is, right? Okay, the total symmetry is conserved. But if I look at the subsystem, in the subsystem, the number of particles is not conserved. However, the subsystem is block diagonal. So there is no off-diagonal terms. There is no way to create a particle out of nothing. So the subsystem will have a well-defined number of particles. I don't know what it is. It is in superposition. It is in a mixture of many different. I can find 48, 49, 50, but I cannot find the superposition of 48 and 49. That's the idea. Okay. When I integrate out part of the system, I will get different possible number of total particles, but it will not get superposition of having 0 plus 1 particle. That will not happen. Okay. That's just the definition of a symmetry. That's not topology yet. What is topology? So topology for this particular type of phases means that the two blocks are identical. So the fact that the blocks exist, the fact that the reduced density matrix is block diagonal, that's always the case. Just this is a definition of a symmetry. However, the topology is sort of a symmetry. It means that there is a symmetry between the two blocks. The two blocks are identical. That's what makes the state topological. And that's what we did on the quantum computer. So in the quantum computer, we basically looked at each of the two blocks separately And we asked ourselves whether two blocks were equal or not. Actually, what we did, we look at the trace of each of the two blocks, and we asked whether the trace of the two blocks is equal or not. And we also asked whether the trace of each block square is the same or not. Let me show you some results. So first of all, the results of the simulation. So the LA, what I'm showing, there is a lot of information here. So LA is the total number of qubits. And here we have, LA is the number of qubits in the subsystem. So I have in total 4 qubits, and I look either at 1 qubit, 2 qubit, 3 qubits, or the entire system. So this is for the entire system. When I look at the entire system, what is red and blue? So red is the symmetric, is the plus block, and blue is the blue block. So basically in this picture, say red would be the plus block and blue would be the minus block. So what you see is that if I take the whole system has a well-defined symmetry. So in the whole system is red. It means that there is a well-defined symmetry. However, in contrast, when I look at the subsystem, I see that in the subsystem, the blue and red come on top of each other. What it means is that the blue and red blocks are identical, meaning that the system is topological. So the topology here is detected by the fact that the blue and red are one on top of the other. So this is just an ideal quantum computer. What happens in a noisy quantum computer? Well, this also works, at least it seems to work, in a noisy simulation. So in a noisy quantum computer, you see that now, well, the symmetry is not perfect because there are noise, but still there's a perfect overlap between red and blue and red. How about the experiment? Well, actually, in the experiment, you see that although the blue and red are sort of close to each other, okay, they are not exactly on top of each other. And actually, we know what the reason is. The reason is what I told you at the beginning. There's asymmetry between 0 and 1. The fact that when I measure, I put more weight on 0 than 1. And so the measurement breaks the symmetry. And if the symmetry is broken, there is no topology. I mean, the topology, in this case, is a symmetry protected topology. It means that it requires to have a symmetry. It first of all requires to have those blocks. Then you can have topology. If you break by hand the symmetry, then no topology exists. So still, the asymmetry is not big. That's why the blue and red are close to each other. So if you say compare the topological case with the non-topological, in the non-topological, you see that the red and blue are completely far off. So this is really non-topological. Here is, I would say, almost topological, right? Red and blue are close to each other. The symmetry is broken just a little bit. So this really raises a lot of questions, of fundamental questions that we haven't been able to address yet. Of what happens when you add noise to a topological phase? How can I, is this topological or not? For instance, let me show you. For instance, you see that the larger you go, forget about the 4. The 4 is it's the total system, it doesn't count. So 1, 2, 3, you see that actually the blue and red sort of get closer and closer to each other. So maybe that's telling you that maybe it's showing some topology. Maybe by doing some finite size scaling, it shows topology. So there are a lot of questions that can be asked. Okay, so that's the end of part number 2. Sorin told me that it's okay if I am a little over time, and I am, but I don't want to be too much over time so that we still have questions for time for questions. So let me do the following. Let me just spend 2 minutes on the first part. If you're interested, then you can ask more in the questions and summarize, because I really want to get to the summary. There is an important message that I would like to convey here. So let me just tell you in words what was the third project. The third project was about time-dependent drives, and in particular periodic drives, and it's related to what is known as Floquet engineering. So Floquet engineering is an idea of using an Hamiltonian that is time-dependent. In this case, would be a circuit that is time-dependent in a periodic way. So you basically apply the same circuit many times, and you describe this circuit in terms of an effective circuit that is different from the original time-dependent one. So you see here you have, say, an Hamiltonian that is time-dependent, and I vary over time in a periodic fashion a magnetic field, and end up in an Hamiltonian, in an effective Hamiltonian that is different. And in particular, we were interested into some peculiar effective Hamiltonian that can be related to long-range interactions. I want to skip this part. If you're interested, I can go back, but Actually, what was nice about this project was a project done with a single qubit. So here we wrote a paper, hopefully it will be published at some point. We wrote a paper with a single qubit quantum computer. Did you say, okay, what is this useful for? And it is useful because this is a quantum computer, a single qubit quantum in which you can address directly the qubit themselves. So not only apply gates, like Hadamard gate, you cannot not only apply discrete gates, but you can really apply a continuous pulse. And that's what allows us to create some interesting state. Okay, let me summarize. So what I would like to put these examples again. These are the examples are just things that we have done, but I think they belong to a frame, and there are other people that work on similar ideas, including Professor Panigrai. What is the idea? So the idea is think of a complicated material or a complicated molecule that you would like to describe. And this is very complicated. It's very complicated to describe it using why? Because the Hilbert space is huge. So you know that in quantum mechanics, the size of your Hilbert space grows exponentially with the number of particles. This is the difference between classical and quantum. In classical systems, if you have n particles, then you have n differential equations or 2n differential equations. If you have 2n coupled differential equations. In quantum mechanics, if you have n qubits, you have 2 to the n differential equation. The size of your Schrödinger equation is 2 to the n, is exponentially large. By the way, this is an interesting side comment, is that although there are a lot of equations, actually this is just linear equations of motion, right? Schrödinger equation is a linear, so you have it's a huge number of equations of motion, but they are just linear. Unlike in the classical case, where you have fewer equations, but non-linear. So, also classical mechanics is complicated, but for a different reason. Quantum mechanics is complicated because although it's just a linear algebra problem, it's a linear algebra problem with a huge matrix that grows exponentially. And you cannot, so how can you solve it? So one way to solve it is using classical supercomputers. Maybe you cannot get to the 100, but you can get to the 10, to the 50. You can get to significant large sizes by using classical supercomputers. And that's something that people do. For instance, in quantum chemistry, they simulate molecules using very powerful classical computers, or in condensed matter. That's also what we do. Another way to proceed is using basically some quantum field theory, some analytical tools, right? We do the renormalization group. We try to describe this very complex, this huge set of equations using some approximation methods, okay? Perturbation theory, whatever, all the tools that we have learned to use have developed in condensed matter. They are very useful. I mean, they can sometimes allow you to describe a system, an infinite system, a system that is infinitely large. Sometimes even the larger the system is, the better the approximation becomes. So these are very powerful tools that allow us to describe sometimes in classical, sometimes in infield, sometimes in normalization group, sometimes perturbative, blah, blah, blah. That's what we do in theoretical physics, right? That's all what theoretical physics do, basically. Another way, and that's really the idea, the original idea of Feynman when he coined the word quantum simulation, is to use another quantum system. So if you have a complex quantum system, then use another quantum system to simulate the first quantum system. Maybe the advantage is that one quantum system is more tunable, and the most beautiful, the best known example, I think really the pioneering experiments were performed in the field of ultra-quant atoms. This is a huge field that you may have heard about. If not, you should really read about it. This is a whole field of physics when you track atoms and you think of the atoms as your quantum particles. You go to very low temperatures, and you see quantum mechanics of particles hopping around. And it's a beautiful system in which you can tune the potentials. You can see single atoms. I mean, it's crazy what they do there. In recent years, and that's what I gave you here an example, there is another system that allows you to do quantum simulations, and it's quantum computers, and in particular quantum computers on the cloud. So you can think of a quantum computer as really a computer scientist would like to think about. It's something that does an algorithm, but you can also think of it as a quantum system that simulates another quantum system. And really, what the really, the power, the best that you can do is really to couple all these systems together. This is what we should really do. We should use materials to learn about quantum computers to learn about classical algorithms to learn about field theories, and so forth and so forth. So it is really the interaction between all these fields that will make science progress. I have no doubt about it. So let me conclude by putting all the references to the works, mentioning the people. That's something I forgot. So I mentioned the students. This Floquet engineering was done by More Roses in collaboration with Guy Landa from IBM. The work about topological phases was primarily done by the graduate student Daniel Latzitz in collaboration with Eran Stela from Tel Aviv University and Robert Rausendorf, well known for his work on measurement-based quantum computers. We also relate this to, so if you read in this PRL, there is also relation with measurement-based quantum computer. And this work about noisy non-local gains was led by the student Meron Sheffer. Yes, so that's it. That's it for my talk. I certainly was over time, but Surin allowed me. Okay. Yeah, I can now pick up some questions.
So thank you, Emmanuel, for the wonderful, wonderful talk. So maybe we can take some questions now. Is this okay?
Yes, I'm here.
Okay, sure. So maybe I read out some.
I'm just telling you that if you don't ask questions, that I'm going to show you the Floquet better. Then you hate me. So if you better ask.
Fine.
I'm open to any question, any suggestion.
Okay, fine. So I have collected some questions. Maybe I read them out. There's a question by Shushant, and he says, when talking about noisy superconducting circuits, what are the factors that make it noisy?
Okay, very good. So first of all, I think it is important to distinguish between gate errors and measurement errors. So when we speak about gate errors, there are, I think, two primarily factors. First of all, the gate. So you want to apply, say, an Hadamard gate. So the Hadamard gate, what it does, it basically takes the zero state and brings it to a superposition of 0, 1. So it's sort of a rotation. If you think in terms of the Bloch sphere, it would be a rotation in the Bloch sphere. Now, and you do that by applying some external pulse, which does this, which rotates this. It's actually in some rotating frame, but effectively rotates the qubit. Now, in reality, the field that you are transmitting to the system is not perfect. So it could basically rotate, instead of 90 degrees, it would rotate it by 49 degrees or 51. So that's one source of error, the fact that the signals that you send are noisy signals. So of course, you need the best, you need to really purchase the best signal systems. And actually, there's a startup company in Israel that is specialized on building a system that creates microwave pulses that then you can feed into your quantum computer. So there is a whole field of having very beautiful, very precise microwave pulses. So that's problem number one. Problem number two is just random electromagnetic fields. So even if you don't do nothing, you just stay there. There are external electromagnetic fields. Say someone enters with his cellular phone in the lab where they are doing the experiment, and some electromagnetic waves are emitted by the smartphone. By the way, this is in the same gigahertz frequency as the quantum computer work. And then if the screen is not perfect, of course they are trying to screen it, the magnetic field as much as possible, etc. But if the screen is not perfect, in general it's not perfect, then some microwave will enter and will just randomly flip a spin or whatever, dephase the spin, etc. So external electromagnetic fields. When it comes to the measurement, then it's really, this is really related to the question of isolation. So you would like, on the one hand, the qubit that is very much isolated from the environment. On the other hand, you want a qubit that is measurable. So the way that the measurement is usually performed is by having a cavity that is next to your qubit. And there is a weak coupling between the qubit and the cavity. And then by measuring the dispersive shift, so because of the coupling, the qubit affects the cavity. So what you do, you measure the frequency of the cavity, and the frequency of the cavity is shifted according to the state of the spin. So you basically just probe the spectrum. Okay, you put a lot of you look for the resonance of your cavity, and the resonance of your cavity is tuned. So on the one hand, you would like to have a good coupling, so you would like to put a cavity that is very well coupled to your qubit. But this will introduce noise, because now all the noise that is in the cavity, the cavity basically it's like it acts as an antenna, right? This cavity is like an antenna that is coupled to your qubit. So if the antenna is too good, then you pick up a lot of noise, and then your qubit dephase. So there is really a trade-off between dephasing and measurement precision. So these are the two, and this also leads to different type of qubits that have been proposed. Depending on the regime, there are these superconducting circuits. They are all based on squids, essentially, or Johnson junctions. But then you can have different regime parameters, whether EJ over C. So the parameters of the Johnson junction are EJ and C, Johnson engine coupling, and the charge energy. So you can work in the regime of EJ over C, large, EJ over C, small. And here there is another factor that you need to take into account, which is the nonlinearity. So in order to have a good gate, you need good nonlinearities. You need a lot of nonlinearity. So this is also another trade-off. So, yeah.
Okay, maybe the next question. So this is by Rahul, and he is asking, how did you choose the cluster state in the triangle game? Are the conditions related to its stabilizers?
Very good. Okay, thanks, Rahul. This is a very good question. I'm really glad you asked it, because now I can address this. This is something that I skipped. Sorry. Can I go? Show slides. Okay, now. Okay, so this one. Okay. So what are the stabilizers? Okay, the stabilizers is actually something that I introduced you, which is this. I didn't call them stabilizers, but they are the stabilizers. So this is this X, Z, X. Remember I told you the cluster Hamiltonian is an Hamiltonian that is the sum over X, Z, X. Remember, that's what I defined as the cluster Hamiltonian. And each of these terms, this X, Z, X, is called the stabilizer. The beauty of these operators is that although they are non-local, so you see each stabilizer acts on 3 qubits, it turns out, and you can do the math, it's pretty simple, that each stabilizer, all the stabilizers commute. So let's say if I take this stabilizer and this stabilizer, they sit on the same qubits, but they commute. So it means that I can very easily find the ground state of the cluster Hamiltonian. I just take the common eigenstate of all these stabilizers because they all commute. So in other words, if the Hamiltonian is, say, minus sum over I x zx, then I take the state in which SI, psi cluster, equals to psi cluster. So I take the state, which is an eigenstate of SI for all SI. This is the common eigenstate of all the stabilizers. Okay, good. So now let's go back to the rules that we had. Okay, so look at these rules. These rules is x1, x3, x5. Okay, now I'm a little bit sorry that I don't have a pen here. But think of taking, how can we do that? Think of these, of taking 3 stabilizers, ZXZ, ZXZ, and ZXZ, such as the Z are the same. So basically, Z1, let me write it in the chat. Okay. So
Emmanuel, you can maybe try.
Chat, you won't see the chat. Okay.
No, it's not a problem. I just wanted to mention that you can annotate and maybe try to use the mouse to write something. Well, if that works, I'm not so sure.
I can try to do that. Let's see if I can do that. So where's my annotation? Annotate. Okay. text. Let's use the text, it's better. Okay, so I take this, I take Z, X, Z. So this is basically Z1, X2, Z3. This is one stabilizer, fine. Now I take another stabilizer, which is Z3, X4, X4, Z5. This is also a stabilizer, right? Then I take the stabilizer, another stabilizer, Z5, X6, okay? And then Z, actually, it should be Z7, but because I have periodic boundary conditions and there are only 6 qubits, actually the 7th qubit is the first qubit. So what I should really write here is Z1, okay? So this is essentially 3 stabilizers. And I know for sure that the state is an eigenstate of each of the stabilizers. So it would be an eigenstate of the product of the stabilizers as well. Now, what is actually the product of this? So I'm taking the first stabilizers times the second stabilizers times the third stabilizer. What I obtain? Well, actually I obtain Z1 cross Z1, but Z1 cross Z1 is just a unity. Right, so it's always giving me 1. So I get X2. Here I have Z3, Z3, it's unity. Here is X4, and then X6. So what I'm telling you is that what I have shown you here, yes, okay. So what I have shown you here is that the product of 3 stabilizers allow me to satisfy the rule. Let's come back to the rules that we had. How do we do this? Okay, good. I come back to the rules. Where are the rules? Yes, here are the rules. Remember, there was a rule that X2, X4, X6 should be 1. And here we go. You see, the product of the stabilizers exactly allows me to, so in fact, what was done was the opposite, the other way around. So first of all, they knew that they had the cluster state, and then they built the rules such that each rule is a product of stabilizer. Okay, this is also a product of 3 stabilizers. This rule is actually a product of 4 stabilizers, and there is a trick that there is a -1 coming out, and that's because when you do Z times X, you get I times Y. So here what they got, basically, if you repeat the same trick, you will see that you get IY times IY. So essentially, the product of the stabilizers is a minus this product. So that's why this product, the X1, Y3, X5, X4, Y5, is actually -1 because the product stabilizer is minus the product. So yes, the answer is all these rules, all the rules were built upon the stabilizers. Okay, so that's for this game. For the game that we proposed, what we did, we asked ourselves the following question. Let's consider, let's for instance take how many stabilizers are there? Question number 1. So there are 64 stabilizers. Sorry, there are 6 stabilizers, right? S1, S2, S3. How many possible products of stabilizers are there? So I can take, say, 1 stabilizer, the product of 2 stabilizers, the product of 3 stabilizers. Overall, as you see, there are 64 stabilizers. So the question number 1 is, so if I take the product of all the stabilizers, the quantum, again, will give me 64. Okay, easy. What is the maximal classical value? That's something was computed here. Turns out is 28. So if you try to maximize this product, because of the minuses that come in the classical game, you get only 28. So it means that the quantum computer gets 64 and the classical computer is 28. So it's 28 over 64. That's the quantum advantage. Then there was another paper by Cadello and collaborators, and they asked themselves, but wait, can I do better? If I choose not all the sum of all possible stabilizers, but I pick up randomly, these products of stabilizers in a way that is best for this ratio, it turns out that there is a sum that has 55 elements, for which the classical rule is 19. So it is really built, everything is built upon the stabilizers. Yes.
Okay, thank you. So the next question is by Aniket. And the question is, are there any examples of quantum computing solving mathematical problems that require an infinite amount of time on classical computers?
Okay, so I think the question is about the idea of, so the answer to this question is yes, and this is what was done by the Google group. in an experiment that they termed quantum supremacy. And the idea is to think about a mathematical task that is relatively easy to compute for a quantum computer, to solve for a quantum computer. Essentially, it's for a quantum computer, it is the most natural thing to do, which is just to prepare some circuit, and the circuit is a circuit that was the easiest circuit to prepare on that quantum computer. So you prepare a circuit, and then you just measure it. And when you measure it, you get an histogram, right? You remember the histogram I have shown you, this 50%, 50%. So therefore, that's it. If you take a random circuit, you will get some random histogram. So that's what you do. You build that histogram, and then you try to reproduce the histogram in a classical computer. And reproducing that histogram in a classical computer will require an exponentially long time. There is a trick that actually, because the histogram is so large, computing the full histogram on a quantum computer is also very complicated because it requires a lot of measurements. So it's easy to do, but it requires a lot of time because you need to measure it. So actually, they did something smarter, which is to compute the correlations between the histogram of the quantum histogram and the classical histogram. That's basically what they did. And they found that there was a good correlation between the predicted histogram and the computed histogram. That's basically the idea. So yes, this is in a sense solving a mathematical problem that takes a lot of time for quantum computers. The problem is one word which is missing, which is useful. So this is a quantum algorithm, but it's not a quantum useful algorithm. So the question, the big challenge, and again, the expectation is that the answer will be given in the next 10 years. Probably closer to 10 than 0, but we don't know. If we have a useful...
Okay. Okay, Manuel, thank you. So the next question is by Shushma, and the question is, for data transmission for farther places, for example, Earth to Mars, there is always a lag in the process. Can quantum computers be used to reduce the communication lag between huge distances?
Okay, here the answer, if I understand correctly, the question, I would say the answer is no.
I think probably somebody has superluminality in mind, and I think that is always associated with entanglement. Maybe that's what.
Yes. So
that's the confusion, or what? Yeah.
Right. So that's, I mean, but I think the agreement. I would say that it's a complicated question, but I think the end answer is that no, you cannot transfer information faster than the speed of light. That's at least this is to the best of our knowledge. This is what happens. So you can create correlations, but you have seen in this example of the two coins. I cannot affect the coin. No, look, I can affect the outcome of the measurement, but I cannot decide. It is still a random measurement. I cannot decide. I can share, if you want. I can share a random number. I can share a random number very rapidly, but I cannot actively tell him what to do. I cannot transfer information in one way. We can create sort of a shared random number very easily, but that shared random number is a random number. I cannot use it. I can use it to encode information. That's what is done in QKD, but I cannot use it to transfer information, to tell him what to do.
Okay, thank you. And the next question, I think, is also by Shushma. So she says, what do you think is the corresponding difference between adiabatic phases and topological phases? So I think there is a confusion in terminology between this Berry phase or adiabatic phase and when you say topological phase. So that's what probably is being referred to.
I think that the problem is that the word phase has a lot of meanings in quantum mechanics, and the way I used it is in the sense of phases of matter. So not phase like e to the I5, that would be, say, related to the Berry phase or this adiabatic phase, topological phase, etc. So that's one whole package. I'm speaking about something else. When I say topological phase, what I mean is a phase of matter. So I mean a set of Hamiltonians that are adiabatically connected to each other. So it's not, yes. But you are right that, yes, right. So it's not, it's in that sense, the topological phase in the sense of quantum, of classification of quantum phases of matter, and not in terms of e to the I5.
Okay. Maybe one more question. So this is by Srijan, and he asks, how the Pauli gates are made? Any short explanation?
The Pauli gates. Okay, so basically, yes, so I think I don't have a short explanation for that. First of all, it depends on the physical implementation. For superconducting circuits, it's not exactly the same as for ions. So roughly speaking, okay, let me give you some very simple and almost wrong explanation. So very simply, but it is intuitive. I think it is good. You know, if you're interested in the details, then this is not the place. But if you're interested, just can I sort of visualize the situation? Think of it this way. Think of it as a superconducting circuit as a ring, and the 0 and 1 state as having current in the ring or not having current. Now, because the current is quantized, as any physical quantity in quantum mechanics, you cannot have, say, classically, you can put as much current as you want in the ring. But quantum mechanically, you can either put 0 quantum, 1 quantum, 2 quantum. So these are the levels. Now, what you do, how do you apply a gate? Let's say I want to do a sigma plus gate. So a sigma plus gate would be something that brings me from 0, from no current, to 1 current. Well, actually, this is not too complicated because you need just to apply a magnetic field, right? You know that if you apply a magnetic field, you can create a current in the superconducting circuits. So that's essentially this is what is done. Okay, again, swiping under the rug a lot of people.
Okay, no, thank you, Manuel. So maybe we're pretty much done with all the questions, but maybe I have a few questions. I will ask one and reserve rest for personal communication. Okay, so I think when you showed the topological, the preparation of the topological state of matter, you did mention that if you are trying to confirm through a quantum measurement that it is indeed what you wanted to make or not, I mean, with what fidelity you have really prepared what you have prepared, then it disturbs, and then you see there was a splitting, there was a small splitting. If you go back to the slide, right? So a very curious thing, you see, when we do measurements, let's say for the quantum Hall state, it is of course a topological state of matter, and within linear response, when we measure conductance, we do conclude that the state is very good without disturbing it. So can we say that most of the quantum measurement within linear response can be brought in within the paradigm of weak measurements, such that the topological state is intact, and I'm still reading off information which gives me confidence that it is a topological state? How should I look at it? Of course, when I'm measuring, when I'm measuring current, there's a quantum measurement involved, and there's a continuous quantum measurement involved because I'm shooting electrons at it and reading off electrons off it. So there should be some measurement going on, but it has to be weak enough that it really doesn't destroy the state as it does in your simulation. So can we think in terms of weak measurement?
I would like to, so first of all, what you say is correct. I would like to maybe make more a comment, which maybe, can be useful. So when you speak about quantum Hall effect, the beauty of quantum Hall effect is that actually it does not require any symmetry, right? Yes. It is just a topological phase of fermions, of say non-interacting fermions, and that's it. You don't need an additional symmetry. Here, these type of phases do require a symmetry, and when the symmetry is broken, then the topology goes away. And this is really what happens here: is that the measurement is the measurement does not respect the symmetry.
I see. So can we say this that, Emmanuel, can we say this that whenever the measurement is such that it doesn't respect the original symmetry, we have trouble? So is there a way to respect the symmetry and still make measurements, or those measurements will always be trivial? Or you can say minimally break it. In a sense, there's optimization which one has to run.
Okay, so one way to proceed could be to say, let's say that we understand that the qubit has a preference towards 0 and 1. So what I could do is to flip my spin before I measure them. See? So I sort of, I symmetrize it by hand, if you want. But then we didn't like that idea, or we post-process, as I mentioned, we post-process the quantum measurement to sort of according to this mitigation procedure. But we didn't like that idea because we said we are cheating. I mean, we don't want to introduce the symmetry that we expect to be there by hand. So
yes. So maybe I put it differently. So this experiment where you are seeing the splitting, can it be brought in the regime where a linear response kind of idea can be incorporated, so that you read off equilibrium correlation functions by doing something which is pushing the system slightly out of its phase, but very slightly, so that you just read it off very carefully. And I was thinking that maybe that.
Yeah, that's a nice idea, actually. Yeah.
Somehow the linear response
correlations in a way that is not a measurement itself.
Yeah, because I think linear response does it somehow. This is the feeling.
Yes,
okay.
no, I understand. The problem is that eventually, so how you do linear response? I mean, the way you do a weak measurement, usually you couple to an oscilla qubit weakly, and then you measure the oscilla qubit. But then the problem is that also the oscilla qubit is measured in an asymmetric way.
Right.
So you see, in a sense, you're measuring the wrong correlation.
Right.
It's an interesting, I don't know, one to think about. It's an interesting idea. Yeah.
Okay. Like thanks a lot again for the wonderful session and the wonderful talk.
Thanks
and patiently, answering all the questions. And hope to see you next time physically in ISA. Yeah.
Absolutely. Yes,
okay.
Yes,
okay. With that, I close this session, and we come back at 3.
Thanks a lot.
Okay. Bye-bye.
Thanks a lot. Really enjoyed your talk. Some more questions I'll send you personally.
Thanks, Professor Panigrahi. It was thanks for the invitation, and thanks for organizing this nice event.
See you. Bye-bye.
Bye. Maybe